Early electrical engineering faced a significant physical barrier, detecting signals so weak they were effectively invisible to standard sensors. This challenge defined the 1858 transatlantic telegraph cable, where electrical pulses were degraded by thousands of miles of undersea travel. Conventional instruments failed to register these messages because they lacked the mechanical sensitivity to react to such minute amounts of energy. Lord Kelvin's mirror galvanometer was the only device sensitive enough to detect those first transatlantic signals, using light to amplify the smallest mechanical movements. The moving coil galvanometer functions as a mechanical computer, designed to convert a chaotic electromagnetic interaction into a legible linear output. This is the modern D'Arsynval moving coil galvanometer, the refined successor to Kelvin's early designs. Its anatomy consists of a rectangular wire coil, permanent horseshoe magnets, a central soft iron core, and a calibrated scale for the needle. When current passes through the coil, the interaction with the magnetic field creates a deflecting torque, forcing the assembly to rotate. But measuring this torque is only useful if the physical rotation of the needle is perfectly proportional to the electrical current passing through the wire. For an instrument to be accurate, it requires a linear scale. However, the natural behavior of magnetic fields makes that linearity difficult to achieve. Consider a basic wire loop suspended in a standard flat magnetic field where the field lines are straight and parallel. In this environment, the deflecting torque is defined by the formula BINA sine theta. B represents the magnetic field strength, I is the current, N is the number of turns in the coil, and A is the area of the loop. The problem is theta, the angle between the magnetic field and the area vector projecting from the coil's plane. As the coil rotates, theta changes, causing the sine value, and therefore the torque, to fluctuate. Even with a steady current, the rotational force varies based on the needle's position. This fluctuation creates a nonlinear scale, where the needle's movement is compressed at the edges of the dial, making accurate measurement impossible. To create a reliable instrument, engineers have to remove the sine term from the physics entirely by changing the geometry of the field. The goal is to lock the angle theta at exactly 90 degrees, no matter how far the coil rotates. This is achieved by using concave horseshoe magnets that curve around the coil assembly. This curved geometry forces the magnetic field lines to bend and point toward the center axis. Then, a cylindrical soft iron core is placed directly in the center of the coil. As a ferromagnet, the iron core concentrates the field lines across the narrow air gap, maximizing the flux density and ensuring the field is perfectly radial. Now, as the coil rotates, its plane is always parallel to the local magnetic field lines. The area vector is locked at a 90-degree angle to the field at every position. If we return to our torque equation and insert this 90-degree angle, the results change. Because the sine of 90 degrees is exactly 1, the sine term drops out. The torque is now simply BINA. By engineering a radial magnetic field, we have removed the geometric variable. The deflecting torque now depends entirely on the current. With a constant deflecting force established, the device needs an equal and opposite restoring force to create a stable reading. Hairsprings attached to the pivots of the coil provide this counterforce. The mechanical restoring torque is expressed as K times phi. Here, K is the torsion constant of the spring material, and phi is the angle of the needle's deflection. Equilibrium occurs when the deflecting torque equals the restoring torque, balancing the equation. BINA equals K phi. When we isolate the deflection angle phi, we can see the relationship clearly. The precision of this balance depends on the material used for the springs. Phosphor bronze is used because it has a low torsion constant, making it sensitive to small forces, and high tensile strength, ensuring it won't break under the weight of the coil. Since the magnetic field, number of turns, area, and torsion constant are all fixed, the deflection of the needle is now perfectly proportional to the current. We have achieved a linear scale. But standard galvanometers cannot measure a discharge that happens faster than the needle can physically swing. The current disappears before the parts reach equilibrium. To solve this, engineers increased the moment of inertia of the moving parts, creating the ballistic galvanometer. While a standard galvanometer uses a low inertia needle for quick response, the ballistic version uses a heavy, high inertia coil. This high inertia makes the oscillation period much longer than the discharge, allowing the coil to absorb the entire impulse before moving. This shift means the instrument is no longer measuring the rate of flow, or current. Instead, the ballistic galvanometer acts as a mechanical integrator. The maximum deflection of its swing is proportional to the total quantity of electric charge that passed through the coil. By changing the inertia of the system, the same physical framework can be used to measure a different electrical quantity. The development of the galvanometer shows how engineering turned the invisible signals of the first telegraph cables into measurable data. The formulas of electromagnetism require specific material conditions to be useful in the real world. Through the use of concave magnets, iron cores, and phosphor bronze, designers effectively solved the problem of nonlinear torque. Ultimately, instrumentation is the practice of using physical geometry to translate invisible electrical forces into a scale we can reliably read.